Okay. Hello everyone. Welcome you coming. So in this session, I will talk about the using Perf and its friend eBPF on ARM platforms. I am Neil Yan. I work for Nilaro support and solutions engineering team. So in this session, we will to mainly talk about the latest status about the Arm CoreSight and the eBPF support in Perf. So we want to finish this session in 25 minutes. So in tomorrow afternoon, we will have the demo in the CoreSight hack session. So if you have interest in that, so you are welcome to join that hack session for the discussing. So for this functionality, actually, they are independent. So I divide the sessions into 3 parts. So first part, we can see that mainly to focus on the Arm CoreSight, the branch tracing with sample flags. The second part only about mainly about the eBPF and how to use the CoreSight to trace eBPF program with the Perf too. The third part is that we want to discuss about how to integrate the Perf for the CoreSight test. So the first part is for the Perf sample flags for the Arm CoreSight tracing. This page we can see that what's the flow for the Perf sample flags. So we can see that in the Perf data, there have the CoreSight data. It contains the CoreSight metadata and the CoreSight trace data. This data, we need to use the open CSD to do the decoding. So it will to output the packets. These packets were to use the synthesize the samples. So finally, this were to output the branch samples. So the output of the branch samples, this will be used by the Perf to do the statistics. Here have the several the fields, for example, the flags, instruction or instruction length. So before that, we don't fill anything into here. So if we set the values for here, then it will to give the Perf to have more valuable information to pass for example, the branch or the instruction samples. So the question is that what we can know from the sample flags. So based on the sample flags, we can get to know what type of the branch. For example, it's for the function call or return, or for the system call, or for the interrupt, extra. So on the right side, we can see that there have some of the defined labels in the Perf tool. It will to indicate what's the branch types. There also have, just now we see that we also can read out the instruction, the bytecode, and the instruction, the side. Basically, that this I think is the more related with the x86 the platform, because the instruction side may be very variant. But for ARM64 or ARM, the platform, usually the instruction size is fixed, for example, 4 bytes or 2 bytes. But we can to read out the instruction bytecode, because usually that for example, for the memory accessing, it also can trigger the data baud, so it can cause the branch. So we can use this way to get more sense for what's the reason to cause the branch. This is one example that for the Perf sample flags. So we can see this column is just to print out the labels, what type of the branch. And at the every tail of the row, we can see that there have some information about the instruction length and the bytecode. The question is that the Perf sample flags actually is just the row information. It's not the how we can use this row information. So this is why that we need to, if we move forward, we need to create the core chain. Here the mechanism is that every the samples, actually we can, based on the flag, for example, if the flag is core. So that means that we can create the thread stack. So if we can see this branch is the core, then we can read out the symbols from the DSO. So then we can push this symbol value into the thread stack. Then if it's return the symbols, then we can pop up the thread stack. So based on that, we can use this way to create the thread stack. I think this here have benefit is that if we use, for example, the tools to do the stack trace, for example, based on DOF, the information actually that were to introduce overhead by these debugging tools. Use this way, actually, all these things have been done for the post-analysis. So this will not introduce the effort for the stack tracing. So finally, we can see that the output result is that we can see for the instruction, we can create the core chain for every instruction. So we can get to know what's the core, like the backtrace for every instruction. So this is the first case. The second case is that for the Perf eBPF program support, we know that eBPF program that is that usually used for the filter. So Perf trace tool, we can specify the -e, we can specify an eBPF program. On the right side, we can see that if we want to use the eBPF program with Perf tool, we need to do some of the configurations to allow the Perf tool to know that what's the clone and what's the kernel build path. So you use this information, the Perf tool can build the eBPF program. But here need to aware one thing that eBPF, we need to use the noder. So Perf tool actually write its own the eBPF noder. So it will to node the eBPF program from userspace to color space. It also will to attach the probe events to the eBPF program. So use this way to run, but it have some extension. This is one example. So we can see on the left side that it just want to probe the color function is high resolution timer, nano sleep. So this is a color function. So use this way, then it will to trace this variable. This variable is actually to access the one data structure element. So here it will to use the probe. This actually is a macro, so it define a section. So Perf tool want to do one thing is that it want to extend the function, the programs, the prologue. So we can see that actually this program actually very simple, just only one sentence. But after the Perf tool to extend this program, actually it will to more complex than the C code. The reason is that we can see it here. The Perf tool will to insert the specific the instruction to help to read out this data structure, and when this function return back, it also want to pass this function the return value, and also want to pass this value to this program. So finally, it will to extend this function. Then it will to allow that the eBPF program can easily to access the data structure elements. So this is one thing that it has the extension. Perf tool now, the best practice, as I know, is that to use the Perf tool with the eBPF program to do the system call tracing. As we know that the S-trace also can be used for the system call tracing, but the S-trace is no performance. The reason that the S-trace rely on the P-trace, so it needs to stop the application. It also, there have many the context switch between the kernel and the userspace to read out the information. But for the Perf tool trace, it want not use the stop the program. It just want to use the ftrace point to read out the system call information. So we can see that the first two, the performance comparison between the DD command, if they have no any trace, the speed is about the 784 kilobytes per second. If we use this trace, then we can see that the performance will downgrade to 22 kilobytes per second. So it's very, very poor performance with trace. So Perf2 here, it wanted to read out the system call, the argument value. There have one thing, difficult thing for it is that there have some arguments in the pointer. So pointer maybe point to some of the string value. So how it can to read out this string value and pass from the CoreSight to the userspace, this is a difficult thing for it. So this is why Perf2 use the eBPF program to help it to read out the string value and pass from the CoreSight to userspace. So this is one example that in the Perf it is used for the system of tracing. So on the bottom part, we can see that here it will every system call where to run into this program, and it will to read use the probe read to read out the system call the arguments. But this is just the raw arguments. There have some string, for example, values. It need to call the BPF tail call. Why it do this thing? Because that it create a eBPF map. The map the system call number with one specific the eBPF program. For example, that it here is that there have open at this system call. It have specific the eBPF program for to handle for this system calls the arguments. So in this function, we can see it will to it know that there have the one point to the string. So it can use this function to read out the string value. Then finally, it will to use this function to output the value based on the Perf framework to output the data from the CoreSight to the userspace. So here I have one thing should to note that usually the eBPF program usually just not to, because it's based on the map. So map, it will not to continuous to output the event from color to userspace. So just to do some of the runtime statistic. Perf2 here have one advantage thing that it can use the Perf the buffer, event buffer. So it can continuous to output the Perf event from color to userspace. So every trace node, it can be recorded and can be output in your space. So this finally, this is the example in the Perf2. You can see that it can trace every system call and output the argument, the values. Okay, so if let's move forward, that if we can to profile the eBPF program with Perf and with the CoreSight, the reason is that eBPF program actually is very low weight, but at the Linux Plumber conference, Acme is the Perf the maintainer. He gave one the presentation is that BPF is eating the world, don't you see? So in that speech, he gives some examples. For example, the XDP, where occupy the CPU bandwidth maybe about 28%. So it's very, very high workload caused by the eBPF program itself. So this is why that we need eBPF actually is debugging or tuning tools, but we also want to profile it itself, can get to know what's the overhead introduced by the eBPF. So for this reason that there have one is BTF, is the BPF time format is introduced. So basically, it wants to encode the debug information for the eBPF program, the data structure and the function. So this allows the Perf2 can read out the debug information from CoreSight to userspace and can annotate the code. So there have some of the, if we want to use the BTF, then there have two tools. The one is the PAHO. This tool is used to convert the DOF, the debug information, to the BTF format. So we can see now in the mainline kernel, if we want to build the kernel, there have the built-in the eBPF program. So usually we need to use the PAHO, this tool. Then if we want to build the eBPF program with the BTF format support, we must use the LLVM 8.0 or native version to support that. On ARM64, there have found one no issue is that usually in the kernel's link script, there have symbol is underscore as text. So we assume that this is the start address of the kernel space. But actually, in ARM64, the kernel, there have several different memory regions have no address than this symbol. So, for example, BPF will also run in one of this region. So this is why that this gives the Perf2 the mistake, the information that BPF not run in the kernel space. So it cannot find the correct the DSO information. So finally, it cannot to generate any samples for the eBPF program. So there have one fix up thing we need to do is that we need to fix up the kernel start this variable in the Perf2. We need to net it to contain the memory regions for these regions. So this after fix that, this one to give one demo is that we want to run the Perf2 to trace the system call. At the meantime, we can run some very heavy workload, for example, build the kernel. So there have many the system accessing. So this way we can know that the eBPF can be hit frequently. So then we can use the CoreSight to trace the eBPF program. So based on that, we can capture the eBPF program, the trace data. So finally, we can use the Perf2 to annotate the eBPF program. So the case 2 and the case 3 is just about the eBPF, but the case 2 just only about the eBPF plus the Perf plus the eBPF. The case 3 about how to use the CoreSight to trace the eBPF program. The next case is that we want to enable the Perf test for Arm CoreSight. The reason is that because there have patches coming for the CoreSight driver or for the Perf2, sometimes they have regression. So we want to use some to find the regression and allow the developers use the same test case to verify the patches. So another thing that we want to allow the test case can be use the same code base with the kernel and with the Perf. So we found that the Perf test, it has the framework. So we just can add some of the testing script. So this allows, for example, the developer to verify their own patch, can simply to use the mainline kernel to test the Perf2 to test the patches. So this is the purpose. Another thing that use the Perf2, we also can verify the CoreSight the tracing data, and also can verify the decoding. These two phase. So this is why that we use the Perf test, these two. So there have one challenge or one thing that actually CoreSight the topology is some kind of complex. For example, if the system there have two cores, if this core it can to output the trace data to ETF, we can simply think this is just the SRAM in SOC. It also can output the trace data through the ETR, so this can output to the DDR. This for just only CPU core 0. For the core 1, it also have the it can be possible to output the trace data to ETF and to ETR. So we need to find some way to cover all the testing for this possible trace paths. So here is just one simple algorithm to resolve this issue, that we can take the ETM 0 is just only for work for the core 0. So we take it as the root of the tree, then traverse the data path with the depth first search. So we can find the data path for ETM 0 to ETF or ETM 0 to ETR. And for ETM 1, also you can do the same thing. So this is just a simple case. Maybe they have more CPUs and they have more things. So we can use this way to cover all the data paths. So finally, we can use the command to specify this. Because here we can specify sync. And we can use the task set, this command, to specify the testing only run which the CPU so can specify it only to output the trace data from which ETM. So the test actually is pretty simple. Just you just can use the perf test list to find out which is the test ID for the CoreSight, and finally you can use the perf test, specify the test ID to do the testing. So here is some of the summary for the current status. So for the perf sum flag, this has been merged in mainline kernel. For the coaching support, now it's just upstreaming. And for perf eBPF program support, this also have some Miller fix has been merged into a mainline kernel. And perf profile for eBPF program, so there have one patch, but this patch has not been picked up by the maintainer because this changed some of the perf core code. So there have some pending. And that's why in the perf test, because this depends on the sysfs node. In the Friday, the Matthew and the Mike will to give some update for this. So after the Mike's patch has been merged in mainline kernel, then this patch will be upstream into the mainline kernel. So this is current status. So I finished. Do you have any question?
So you can build with C-Lang now? You said you could build with C-Lang now, so you don't need to use BCC anymore?
Client, you can use the client, right?
Yeah.
Yeah. So use the eBPF, we must to use the client. We cannot use the GCC because GCC have no the eBPF.
No,
okay.
BCC, the one that's done by Greg from Netlink.
Oh, yeah. BCC is more complex. More the I think is more include more the test shoots, and it also contains the Noder and that kind of thing, and it can support the advanced language, for example, the Python or Lua, this kind of thing. I think the perf now support the eBPF is pretty simple. So it's just to support very, very simple the functionality, for example, for the system call trace. It cannot support, for example, memory or file system.
Okay. Yeah. So in that case, you have to use still the BCC stuff.
Okay. Yeah. So I think for the performance, the profiling, just for general profiling, can be used the BCC. But if you want to capture every trace event, I think you should rely on the perf event. It can output the every perf event based on the buffer. Yeah.
Okay.
GCC will have support from version 10.
Oh, okay. Sorry, because I'm not a teaching guy. Sorry. Yeah. Thanks. So.
Oh, and one other question.
Yeah.
You said for the machine translation to kernel start, is that for all ARM platforms? Is it ARM general or is it specific chipsets?
You mean the CoreSight topology?
Yes, the one.
This one?
No, going back. That one over, next one. You were talking about that. Is that in general for any ARM platform? Is this a common thing or is this?
No, this is not a common thing. For example, x86 or the ARM's 32 platform, they don't have such kind of thing because it's pretty simple that BPF region just the kernel maintainer, ARC maintainer reallocate up this address. But just for the ARM64, they allocate previous this symbol. So yeah, just specific for the ARM64. Okay, so that's that. I appreciate that Matthew, Mike, Nietzsche, and Rob, and Suzuki, and Al, they review my patch and help me to upstream this patch. So I appreciate it. And thank you guys much for coming.